have one of the faculty members from Pitt here to help us learn a little bit more about statistical collaboration. So Dr. Scott Rothenberger is an assistant professor of medicine in the Division of General Internal Medicine. He is a faculty statistician at the Center for Research on Healthcare Data, which is an entity that supports University of Pittsburgh faculty members conducting high quality clinical and translational research. His methodological interests include the design and analysis of clinical trials, analysis of claims and electronic health record data, longitudinal data analysis, and time series methods. He collaborates on studies in areas such as women's health and behaviors, pregnancy care, endocrinology, pharmacoepidemiology, and sleep medicine. Importantly, Scott enjoys mentoring and collaborating with early career investigators, and that's how we were lucky enough to have him come speak today after one of our faculty members, Dr. Kramer, had sessions with Scott and found them very helpful. He recommended him, so appreciate that. Scott serves as a statistical mentor on several career development awards, and he finds these relationships very rewarding. He's also the assistant director to the Data Center for Early Career Collaborations, a role through which he collaborates with junior investigators and provides statistical support for their funded projects. He is also the director of multiple courses at the Institute for Clinical Research Education, the ICRE, and truly enjoys teaching as well as mentoring his students. So with no further ado, we welcome Dr. Rothenberger to our PEAC session today. Thank you.
Great. Well, it's great to be here, and I look forward to discussing optimal strategies for collaborating with a statistician, as well as general considerations that you should be making when thinking about your project and things that you can discuss with your statistician that you form a collaborative relationship with. So here, let me actually, give me 1 second to make sure I can share my slides right. Sometimes I accidentally hang up by accident.
We can see your slides.
Yeah,
Great.
we can see it. Thanks.
Perfect. Perfect. Get the Teams window out of the way, and I'd be ready to start. All right. So, yes, I am a statistician and an assistant professor of medicine and clinical translational science. And I really enjoy giving talks on how to collaborate with a statistician, what kind of things you should consider. And this is very much a crash course into all the things that you may want to consider whenever working with a statistician. So keep in mind that this is not an end-all manual for every single aspect of collaboration. Okay, so I'll get started first with introducing what is the difference between collaboration and consultation? Well, one person, her name is Judith O'Fallon, said, in order to be effective, medical statisticians must function as collaborators, not consultants on projects. What that means is that we should not be viewed as service workers. We should not be viewed as someone that you come to at the last second with the requests, thinking, that we would be able to just understand everything about your study and produce a quick answer. We're not consultants where 1 hour could cover every single aspect of your study itself. In fact, we should think about statisticians as collaborators, co-Is, co-investigators on your grants and on your projects. We work with you throughout the entire research cycle. So my quote or definition of collaboration versus consultation is the amount of time or lack thereof that I'm given to work on a project is directly proportional to the quality of the end product. So that's from me. And the key to take home is the earlier you start working with a statistician, such as myself, the more that we end up producing a really high quality product in the end. We end up producing something that's scientifically valid, produces meaningful results, and is robust and makes sense statistically. So first, just going to start with what are some common questions that I'm asked when starting a collaboration? And that's going to be question 0. When should we meet? Okay, now as I go through this, I welcome people to pull themselves off of mute to help answer any questions that I may ask. So first, I'm going to give 4 possible scenarios of when you may want to meet with a statistician. So scenario A, I got my paper back and a reviewer said my stats were wrong. So let me reach out to a statistician and try to fix this real quick because I have a 2-week turnaround. Well, that's one option. Okay, another when should we meet type question is when I don't know what to do with the data that I've already collected. Another option, 1 week before a grant deadline, reach out and only ask for a sample size calculation to power your entire study. 1 week before you're submitting the grant. Finally, when I'm developing my study, at the very beginning of the development stages of your study. So what would you think would be a reasonable answer as to when we should meet?
I'm going to ask you, have A, B, and C happened before?
A, B, and C happen a lot to statisticians. We get requests a lot in the nature of A, B, and C, and sometimes we're able to help out. However, option D is the optimal strategy. Meet with a statistician and start a collaboration when you're developing your study, even in the very, very initial crude stages of thinking about what you're going to look at and how we can help as statisticians and work together with researchers such as yourselves to actually be able to answer the questions that you're posing. So it's really important to reach out as soon as possible in the earliest stages, because if you go too far along with the project and then you're asked for, say, a quick turnaround on a manuscript, but they said the stats were completely wrong, a statistician will have a very hard time collaborating with you to be able to turn that around in time, because they may actually have to start from the beginning to understand your study and catch up to be able to even advise you on how to do stats or do them for you. Okay, I actually noticed that a hand was raised. However, I can't see the chat.
Sorry, it's me. Sorry, I'm Lingland. I'm in the Department of Pediatrics. I actually have we have 2 statisticians in our research group, but I find that one of the problems is you're sort of building a culture. The fact that you like to work with junior faculty is extremely helpful, but I think the problem is that when we have new fellows, for example, who are starting projects, it is always best to make sure that like you understand what measurements, what your primary endpoints are, what the type of data your primary endpoints are in order to calculate the sample size. So the problem I find is that they oftentimes have difficulty accessing statisticians because part of this is learning how to do research, right? And to do it correctly. When they don't have access to statisticians because they're limited by access to statisticians, it's very hard to engender the right culture of how to frame a study design correctly. So how do they do that? Because UPMC, unfortunately, is difficult with this situation.
Mm-hmm. So at least on the PIT side, because I'm technically not a UPMC employee, but on the PIT side, there is the Center for Research on Healthcare Data Center, and we have several biostatistical and qualitative methodologists that can collaborate with fellows on their projects. There's also the CTSI, which they have some rules, but the CTSI at the University of Pittsburgh also offers up to 10 hours of free consultation and then can work with you to extend that depending on the needs of your project. However, I use the word consultation in there, so that signifies that they're putting an hour limit on it, and it might not be a full collaboration. However, if it is a smaller project, smaller in scope, talking to the CTSI, you may find that they may be able to suit your needs. Finally, the university in general is recruiting biostatisticians. In fact, my own research group at the Center for Research on Healthcare Data Center, we're looking to recruit at least 2 new faculty members to be able to accommodate the needs of people who are not able to find statisticians, because that does seem to be an issue lately. You're very correct, is we need to find better ways to be able to provide access to statisticians, and ways that don't necessarily cost too much. And I saw another hand go up.
Yes, it's me. I have a question, and then I'm gonna, Mary put in the chat, Mary Chapman, sorry, my mic doesn't work. Can someone repeat those resources for consultation at Pitt for collaboration? So I know it was CTSI certainly, and that you go through the website and put it in a quick brief synopsis. And then how do we access the data center, and what's the, like, what would be the best way to connect?
So actually, a lot of these questions that are being asked, I'm going to cover some of them as I go along. However, with the CTSI, you're correct. Go to the Pitt CTSI website, and they have a core called the Bird Core. And that's what you would want to focus on if you want to go the route of CTSI. If you want to work with the data center, I am actually someone that you can reach out to, and we have as well several master's level statisticians as well as faculty level statisticians, and we can work together to try to set something up that would suit your needs. So my email address is actually rothenberger@pitt.edu. So it's just my last name @pitt.edu. And feel free in the subject line to mention that you were attending this seminar and you're interested in trying to form a collaboration.
And then I'll put in a last, I guess, offering that recently the CTSI, because of bandwidth, stopped being able to support medical education research. And so through the Department of Peds, and with the help of Alejandra Hoberman, we have pulled together the statisticians that are part of our Department of Pediatrics, who are funded by our specific faculty members' grants, but they're willing to potentially help out with medical education projects, and prefer, just like Scott's pointing out here, to be doing it as option D.
As early as possible.
Thank you.
Yes.
So reach out to me if you have questions about that, and I will try to connect you.
Yes, I may be reaching out with questions about that, so I know how to work with that as well. So thank you. That's good information to have. Sometimes the Pitt UPMC disconnect makes it a little hard to see the ways that we can work together.
A lot of it hard.
Exactly, including trying to log into Teams and be on the right institution. So, all right. So let's see, what do we need to do when we're preparing for a collaboration? So when you're preparing for a collaboration with a statistician, you really need to think about, and this might seem, obvious. However, you'd be surprised how often people don't really think these things through thoroughly before collaborating with a statistician. What is your research aim? What is your research question? Do you have hypotheses? What are you trying to accomplish, basically? What you're trying to accomplish and how you try to accomplish it, as well as what you expect to get, will guide the collaboration itself and what we do. Now, something to keep in mind is that as you're thinking about things before an initial meeting for collaboration with a statistician, is that these do guide the entire research process. However, they don't need to be final. That's our job as a statistician, is to help you fine-tune and refine your aims, questions, hypotheses. And over time, we end up producing high-quality work, as long as we all hold up our ends of the agreement for the collaboration. So how do we, continuing on from the previous slide, prepping for a collaboration. So about 1 or 2 weeks before an initial meeting, or even more time, The more time, the better, not the day before. It's good if you could send what your preliminary version or draft of your aims are, what your hypotheses are. If you have an idea of what study design you want to use, send the proposed study design as well as details that might be involved, information about how you propose to collect your data. That's always important. If there's any kind of sample size considerations that need to be taken into account, let's say you don't have to produce a sample size calculation yourself before meeting with me. However, if you want a sample size calculation or need one for your work, if there are feasibility issues in terms of, say, the total number of people you could even recruit, let's say that you can only recruit a total of 100 people total. Let me know that so that I can work with that information to produce a reasonable power estimate for you. Finally, any relevant articles that deal with your area of science, because as a statistician, we deal with so many areas of science, we can only be a little bit of an expert in some of them. Make sure that you give some background into the area of research that you're looking at. For example, articles that have a study that's similar to the one that you're proposing. That would be good to have. Okay. So after we got past question 0 of when to meet with a statistician and why it's important to, we have to think, okay, so what should my study be? What should my study design be? What should it look like? Do I want to collect cross-sectional data, which means that you take data, just a slice of time, and, for example, look at the correlation between one variable that you collect in that slice of time and another variable? Can IQ predict performance on the MCAT? And you just collect data from one individual with those two measures, and you do it just at a single point in time. There are pre-post studies with a comparison group, and there's also pre-post studies without a comparison group. So pre-post study with a comparison group, I should actually start with pre-post studies without a comparison group, would just be to see, does one group of individuals, do they change from, say, a pre-intervention to post-intervention in relation to some kind of outcome that's meaningful for you? Now, another way that you can even boost that study design up is to also include a comparison group, where you look at the pre-post difference in the comparison group. And the benefit of that is that you can compare the pre-post difference in your intervention group to the pre-post difference in your control group, so that you can confidently say it's not just a maturation effect, or people aren't just getting better over time for other reasons. Another consideration, more than 2 time points. Do you have longitudinal data? Are you tracking people over multiple time points? Are you looking at how things evolve over time? Are you looking to do a randomized controlled trial? Are you looking to actually pull off an RCT? So these are all questions to think about that start guiding you as to what could my study design be, or what should my study design be? So how do we answer? What would be the optimal study design? Well, the answer depends. And what does it depend on? Well, it depends on some of the factors that we've actually been talking about already. Study design considerations. So think about, what are your outcomes? You need to make sure that your outcomes are clearly defined, that they're measurable, and that you're not proposing too many of them. There's no set rule as to how many outcomes you should have. However, if you list 30 outcomes, it becomes almost intractable to work with. So it's good to have a reduced set of outcomes that are most meaningful. You have to think very carefully about, what are your exposures or interventions that you're looking to see? Are they effective? You also have to think, what other variables should you consider in the analysis of your data? Are there possible confounders that might be explaining some of the relationship away that you're observing? We want to be able to control for those. Are there mediators? Mediators would be intermediate variables that lie in the causal pathway between intervention and outcome. There may be, for example, some intermediate process that actually explains what's going on. So if there's the potential for mediators, you need to think about that as a variable to consider as well. You may need to make special adjustments to our models to be able to accommodate mediators. And finally, moderators. Moderators are variables that define different groups that may have different intervention effects. So if you suspect that one race subgroup may have a different intervention effect than another race subgroup, then you need to consider race as a potential moderator of a treatment or intervention effect. So these are all things you need to be brainstorming about as you're thinking about a possible study design. As well, think about how are these things measured and when are they measured? Does it make sense? Are you measuring things at appropriate times? And even a very simple one is make sure that if you have, say, predictors, that predictors come temporally before your outcomes. That way you're not just trying to show reverse causality or accidentally show reverse causality. Think about how are they analyzed in similar studies. How people do things in other studies that are similar to yours may be a very great guide for what you should do in your own study, and then you can add some of your own novelty. Finally, think about, are you looking to do more of just a needs assessment and just say survey a group of a sample of people in terms of their attitudes, confidence, and beliefs in certain topics? Are you doing a pilot study that has a very small sample size and you're just trying to demonstrate that it's feasible to do a larger study? Are you doing an exploratory study where you have a lot of data, but you don't have necessarily set hypotheses as to what the relationships of the data are? Finally, there's confirmatory studies, which are follow-up studies to previous studies to confirm results that were observed by others. So you need to think, are you confirming a result that was already established by someone else? Are you looking to establish hypotheses that you can explore in the future? Are you doing a simple needs assessment or a pilot study? These are all things to think about and outline out before meeting with the statistician. Okay, now we're going to get into a little bit more of statistical considerations. People always ask, or often ask, how should I evaluate Interrater reliability? So what is Interrater reliability? So it would be the degree of agreement that you have among independent raters. So let's say that you have two people independently rating someone's presentation, and you ask them to rate the quality of their presentation as being low, medium, or high. And they do their ratings separate from each other. Let's say that they do that for a bunch of presentations. You want to then see how much do the two raters agree with each other in an overall sense as to whether it's a low, medium, or high quality presentation. Well, the ways that you can address this, if you have, say, categories like low, medium, and high, two of the most common methods are Cohen's kappa coefficient, as well as just simple percent agreement. What percentage of the time do two raters agree with each other? That's often a very simple measure of agreement. The Cohen's kappa coefficients, which there's a little bit of a complicated mathematical expression for it, but you don't really need to know that. Cohen's kappa coefficient, in a sense, adjusts percentage agreements by the amount of agreement that you could achieve merely by chance. So if you were to randomly be selecting what's low, medium, or high, Cohen's kappa takes that into account. So Cohen's kappa is typically preferred over percent agreement. However, both are commonly reported. Now let's say that instead of just having low, medium, and high as categories, you have some kind of continuous variable. And it can range from 0 to 30. Let's say that you rate quality on a scale from 0 to 30. A commonly used measure of interrater reliability for something like that is the ICC, or interclass correlation coefficient. So if you're trying to choose which one should I use, especially if your categories tend to get a little bit more granular than low, medium, and high, and you might want to start analyzing them on a numerical scale instead, those are things that you have to really think about. And the answer depends on what is being rated. What is the scale? How are you measuring them? Low, medium, high? Or are you doing continuous? And a statistician will help you in deciding with this and deciding on the best measure that you could use. I see this a lot in medical education projects where they have raters rate, say, standardized patient encounters. And they want to see how much do two raters agree in terms of an assessment of an SP encounter. And they need that to be able to say that two people independently rating it can come to the same conclusions. So quantifying inter-rater reliability is a question I do encounter a lot in medical education research. All right, another one that I get often is, how will a low follow-up rate affect my analysis? So let's say that you just have a pre-post design, a pre-survey, you implement an intervention, and then you gather a post-survey with the same questions. Now let's say that you have a total of 60 responses pre, but you only get 35 people to respond to the post-survey. So, can you actually do a valid analysis of just the 35 paired observations? Additionally, is there a way that you can still utilize data for the other 25 people? And that's a question that people often don't ask themselves when dealing with paired data. They often think, I have to have pairs of data, therefore I'm limited just to my 35. But with some more sophisticated statistical techniques, you may be able to utilize data from everybody at all time points. First steps in doing that is you have to investigate potential reasons for why you have missing data. Now, I'm going to introduce a term, and there could be entire lectures on missingness mechanisms. But if your data are missing at random, we can still do an analysis using all 95 observations, the 60 pre and the 35 post that you actually obtained. You wouldn't be limited just to the 35 subjects with complete data. So you may be asking, what does missing at random means? It means that if you can identify some observed quantities that you have measured that can explain the missingness, you can incorporate those variables that may predict missingness into your model and arrive at valid conclusions. So missing at random means generally that once you know what variables you have that could predict missingness itself, if you incorporate them, you can use a technique such as mixed effects models, if you've ever heard of that. It's sophisticated modeling techniques. We can actually account for that. What we don't want to encounter is a situation called missing not at random, and that's where you have missing data that the missingness depends on a value you would have observed had you observed it, but you didn't observe it. For example, let's say that you're looking at a study investigating a disease, and patients are getting sicker and sicker as time goes on. As assessment time points goes on, less and less patients are reporting back to be asked about their symptoms. Well, what happens if someone doesn't report or fill out an assessment because they're too sick to do it? If they're too sick to fill it out, then the fact it's missing is related to a sickness that you didn't observe. That would be a case where this would not work. Sum up all of that, there may be a chance you can use all 95 observations and talk with a statistician to see if that would be appropriate. We can work on missing data with you and try to see what we can do to incorporate as much information as possible. All right, now this is another one that is all too commonly missed, is people need to ask themselves, why visualize your data whenever you do have data? This is just a general statistical consideration that you really, really need to take seriously. So why graph your data? Well, graphing your data, for example, using histograms, that allows you to identify the shape of a distribution. The shape of a distribution is really key to being able to determine what kind of analyses are appropriate. It also allows you to identify potential errors or outliers in your data set. The shape of the distribution guides which numerical summaries you should use. For example, should I report the mean? Should I report the median? Which ones would be most useful? You can get that information, or you can gauge that information from just looking at a graph of your data. And finally, as I alluded to, looking at your data is a first step in actually determining which statistical methods or tests may be appropriate for your particular research study. So in terms of shapes of distributions, this may be familiar to a lot. It is a good idea to go over 4 commonly encountered shapes of distributions. So in the upper left-hand corner, notice that we have data that looks symmetrical. It's the same from the midpoint, looks like it's a mirror image in both directions. In the upper right, we have data that has 2 humps. In the bottom left, we have data where a lot of values are collected at, a lot of observations are collected where the values are very high. And there's very, very few observations with low values. And finally, in the lower right-hand corner, that's where you have a lot of observations with really low values and a very few observations with really high values. So we often call those shapes symmetric in the case when it is truly symmetric. A normal distribution is an example of a symmetric distribution, bell-shaped. We call the double hump distribution a bimodal distribution, and a bimodal distribution may actually indicate to you that there's 2 different populations going on. There's 2 different types of effects going on, and so when you look at it, maybe those reflect 2 different population distributions. When you have data that there's a lot of high numbers and very few low numbers, and it trails off to the left, we call that skewed to the left. And similarly, whenever we have a lot of observations with low values and very few observations with high values, we call that skewed to the right. So again, why does shape matter? Well, if you look at this, most all of the observations in this left skewed graph, in the right skewed graph, most of the observations are clumped toward low values of the variable that you're looking at. So the vast majority of the values you're looking at are low. However, if you look over here, there are a few observations that are really high in value, and they could be valid observations and not errors. They may be outliers, and outliers aren't always errors. The reason that we call the bulk of the distribution the trivial many is because, yes, most people would fall into that category compared to the vital few, which are the really, really outlying observations. The vital few will produce a lot of influence on summary statistics that you can generate, descriptive statistics. One example, if we tried to calculate what's the average value of this variable, what's the mean of this variable, those vital few are going to pull the mean really far to the right, to the point where the mean looks like it doesn't even reflect the vast majority of the data from the trivial many. So why does shape matter? If it's very skewed and you just report a mean, the mean or average might not be all that meaningful because it doesn't reflect what's going on with almost everyone in the population. All right, so here are examples of what we've been looking at. Whenever you have data that's skewed to the right, you're going to find that the mean is going to be greater than the median. The more those vital few pull the more vital few that you have further and further out, the more of it the mean gets pulled. However, the median, which is the 50th percentile, will stay the same. So when you have skewed data that's skewed to the right, you're going to find the mean is greater than the median, and the median is a better measure to report. It's more robust. When you have symmetric data, for example, normally shaped data, then you have that the mean and the median are the same. The average value and the 50th percentile fall straight in the middle. Finally, whenever we have data that's skewed to the left, we encounter a situation where you're going to have the mean being less than the median. And the more the skew, the more that the mean is going to be less than the median. In this case as well, you would want to report the median instead of the mean, because the median is more robust in the face of skewed data. Any questions so far? I know this might seem a little basic, but trust me, people actually forget to think about these things. And next, I'm going to show another example of why we should visualize our data instead of just running with code and looking at descriptive statistics and numbers alone. So this is a hypothetical example. Suppose we have 4 data sets. In each data set, we have 11 pairs of X and Y values. Let's say, for example, X could be IQ and Y could be MCAT performance. And let's say you want to predict MCAT performance based on IQ. So we have 4 data sets, and we have in each data set 11 pairs of such data values. Now, I'm going to tell you up front that the 4 sets of X and Y values are not the same. The values of X and Y in each of the data sets are different. Now, let's say that we're interested in fitting regression lines for each data set where we have Y as the outcome and X as the predictor. So best fit regression line, simple linear regression, where we have Y equals the intercept plus the slope times X. So what we're going to do here in the next couple slides is we're going to first just compute some basic numerical summaries for each set of X's and Y's and perform linear regression on each data set to find that best fit line for that data set that is supposed to represent the relationship between the predictor and the outcome. Okay, so let's say we call the values of X and Y from set 1, X1 and Y1, the values from set 2, X2 and Y2, so on and so forth. And let's say we calculate the mean of X within set 1, the mean of Y within set 1, the standard deviation of X within set 1, standard deviation of Y within set 1. And finally, we also compute the correlation between X and Y within set 1. And then we do that separately for each of the 4 sets of data. Now, with the set of data points that I actually have, let's say that we actually obtain these means and standard deviations that are shown here, as well as the correlations between the X and Y values. If you notice, within out to 3 decimal places, the means of the X's across the data sets are all the same. The means of the Y's in each of the data sets are all the same. The variation of the standard deviation for the X's are equivalent across all 4 data sets, and same thing with the Y's, out to 3 decimal places. Finally, if we were to, those bottom 2 rows should say correlation of X3, Y3, and correlation of X4, Y4. I can correct that and send an updated one for that. All 4 correlations from the separate data sets produce a correlation of about 0.82. So they're virtually equivalent. What we're finding, what we're seeing here based on simple numeric summaries, is that the 4 data sets look like they may be virtually equal based on very commonly used descriptive statistics. So let's say that we run simple linear regressions on each of the data sets in our software, and we obtain fitted intercepts and slopes, as well as a p-value representing the significance of the relationship. And we do that separately for set 1, 2, 3, and 4. Well, with the set of data points I have, I end up getting that the intercept is 3 for all 4 data sets. The slope is 0.5 for all 4 data sets. And the p-value is 0.0022 for all 4 data sets. So these are all indicating significant relationships between X and Y, and the estimated or fitted regression lines that we get are all equal. So far, it's looking from these just basic number things that we might be seeing the same relationship in each data set. However, like I'd said, we need to consider visualizing our data, not just running with code to get numbers. Keep in mind, those 4 sets of data do not contain the same values. There are 11 XY pairs in each data set. We had all the sample means and standard deviations for X's and Y's equal to each other, as well as the correlations are all equal, slopes and intercepts were all equal, and the p-values were all the same. So are the true relationships underlying all of this the same? Let me show you what the 4 data sets actually look like. I'm going to overlay the raw points with the fitted regression lines themselves. These 4 data sets that contain different values of X and Y all produce the same best fit line to represent the relationship that you're trying to investigate. Now, let's take a look at a couple of these. In the upper left-hand corner, it actually looks reasonable that a linear relationship is going on. And it doesn't look like there's any kind of systematic deviation of the observed data points from that fitted regression line. So it looks like actually maybe appropriate, likely appropriate to do a linear regression and trust our results for the slope and intercept if we're using that upper left-hand set of data, set 1. However, if we look at set 2, take a look at the observed points. That looks like a quadratic relationship. That looks like a relationship where the observed data is going up and then it's curving back down. We're trying to fit a line through it. Does a line truly capture that relationship? No. The relationship should be captured by a regression that includes a quadratic or polynomial term, that includes the ability to capture a nonlinear effect. In the bottom left-hand example, set 3, we have one data point that's extremely outlying or influential, that's pulling the regression line upward compared to all the other data points. That actually may not represent the relationship going on with most of the data points, because one data point is unduly influencing the best fit line. Finally, in set 4, we have a case where 10 out of the 11 values were measured at exactly the same values of X, and only one value of X, close to about 20, was there a value of Y measured. And so the best fit line for this regression would be connecting straight to that dot near X equals 20. So that dot near X equals 20 is totally driving that line. And we don't have any points in between those 2 values of X. So we really don't know if there's a linear relationship going on. If you'd measured it at different values of X, you might end up seeing a different pattern. It might be quadratic. Take-home point, visualize your data to see if the relationship you're trying to fit actually reflects the truth in the data that you saw. All right, so big question I often get. What statistical test should I use? Now, these are just bare bones, crude guidelines. So keep that in mind. But first, ask yourself, do you even need to perform a statistical test? Sometimes you don't need inferential statistics. For example, often in needs assessments, you just calculate means and standard deviations of variables of interest. Often you don't have necessarily comparisons that you want to do formally. You just want to see, gauge what is the, what's the environment, what's going on currently to identify possible needs for future interventions. Also, if you have, say, a pilot study that's going to be used to inform a larger study, often descriptive statistics with confidence intervals is enough. And you focus more on precision than you do on significance. And in many cases, descriptive statistics are all that you may need. In terms of continuous variables, descriptive statistics you could consider. If you have symmetric data, means and standard deviations are good. Means and standard deviations would accurately represent what's going on in your data set. If you have skewed data, then medians and interquartile ranges. Interquartile ranges is it's the span between the 25th percentile and the 75th percentile of your data. Means and interquartile ranges are robust to skew. So if you have skewed data, report medians and IQRs. Sometimes full ranges of the data are also reported. Confidence intervals, they're useful for both skewed and continuous data. For categorical variables, we pretty much have frequencies and percentages. And you can also calculate a confidence interval for, say, the percentage that fall under a particular category. So confidence intervals are also useful in this case. So I bring these up because we have to consider again whether we have symmetric or skewed data, as well as what type of categorical data do we have. So here's going to be one of those sort of flowcharts of statistical tests that you could print out and keep in your back pocket as a quick reference. And again, happy to share these. So say that you have a continuous outcome. And if you have a Likert type scale, often continuous outcomes are fit that way as well, with continuous Likert type data. You have to consider two main things when thinking about what type of statistical procedure should I use. First is, do you have paired data or unpaired data? Paired data means data coming from the same individual, just measured at different time points. Unpaired data are data from independent groups of individuals, and you want to compare the groups to each other. And remember, I said your continuous outcome can be skewed or normal. We have to consider whether it's skewed or normal. So as I work through this, hopefully by the end, it'll make a nice diagram. Let's consider the case of when you have paired data. First, think about, do I only have 2 time points? Is it pre and post? Or do I have greater than 2 time points? Do I have a pre, a post, and a delayed post? Now, when you have unpaired data, you have to think about, do I have 1 group? Am I comparing 2 independent groups of people, where the people are not the same in the groups? Or do I have greater than 2 groups of people that I want to compare? Now, we can take a look at, let's say, for the paired data situation. If you have skewed data, what do you do? And if you have normal data, what do you do? Well, the type of test that's often used for skewed data when you have only 2 time points and paired data is called the Wilcoxon signed rank test. Now, if you have 2 time points and you have normal data, you can use what they call a paired t-test. I'm sure most people have heard of that. The Wilcoxon signed rank test is an analog to the paired t-test, but just for skewed data. Now, let's say that we have greater than 2 time points and we have paired data. For skewed data, you can use a technique called Friedman's test. There are other variations. However, that one's commonly mentioned. Now, if we have greater than 2 time points with paired data and we have normally distributed outcomes, you can use what's called repeated measures ANOVA. Now let's consider the case of unpaired data with various number of groups. So if you have skewed data and you only have 1 group, let's say you want to compare the mean of 1 group to a value of 0 to see if it's significantly different from 0. With skewed data, you can use a 1-sample Wilcoxon signed rank test. For normal data, you can use a 1-sample t-test. When you have 2 groups and you have skewed data, Wilcoxon rank sum. For 2 groups and normally distributed data, you can use a 2-sample t-test. Now, if you have greater than 2 groups and you want to compare the means between more than 2 groups, for skewed data, the way you would compare measures of central tendency would be with the Kruskal-Wallis test. You have normally distributed data, you can use ANOVA, or analysis of variance. Analysis of variance is the extension of the 2-sample t-test to multiple groups. Now, this doesn't cover everything by any means. So if you have some combination of both paired data and unpaired data, for example, if you have 2 groups with 2 time points, or let's say that you want to adjust for potential confounders, then other methods you may want to consider are linear regression, mixed effects regression models, and models that are called generalized estimating equation models. Speak with a statistician if you want to go that far. We'll help you determine what's appropriate to do. Things are a little bit easier whenever you have categorical outcome, and I'm going to focus on binary outcomes. What type of statistical test should you use if you have, say, a binary outcome? Now, again, we do have to consider paired data versus unpaired data. Are they data from the same people or data from independent groups? We do not have to consider whether the data are normal or skewed when dealing with categorical data. We only have to worry about that for continuous data. Keep that in mind. That's what makes this diagram slightly simpler. So if you have paired data and you have 2 time points, let's say pre and post, or you have greater than 2 time points, we also have the case of unpaired data where you have 1 group, 2 group, greater than 2 groups, just like on the previous slide. Well, to analyze paired data where you only have 2 time points, you can use what's called a McNemer's test for paired proportions. Whenever you have paired data with greater than 2 time points, one test that's used is called Cochran's Q test. Now, whenever you have unpaired data, meaning independent groups, if you only have 1 group, you can do a binomial test of proportions to see if a proportion is significantly different from some pre-specified value. If you have 2 groups, you can use the all-familiar test, chi-square test, or Fisher's exact test, which is it's a slightly non-parametric, or how should I say, more flexible test than chi-square that doesn't rely on as many assumptions. Whenever you have greater than 2 groups, you can also use chi-squared or Fisher's exact test. It works for 2 groups and greater than 2 groups. And if you have some combination of both, again, let's say that you have 2 groups, 2 time points. Let's say you want to adjust for potential confounders. You can use what are called generalized linear mixed effects models, which are just mixed models for categorical data. Again, you can use something called GEEs, generalized estimating equations. And you can also consider something that might sound a little bit more familiar, logistic regression with a binary outcome. Logistic regression with a binary outcome is similar to linear regression. It's just that your outcomes are 0s and 1s. All right, so any questions on that? We're almost through. I know this is a lot to take in, so that's why it's good to have these resources after we're done with the presentation. So remember, what are you looking to do? Are you looking to do a needs assessment, a pilot study? Are you looking to evaluate a curriculum? Are you looking to evaluate policy implementation? Each of these things may involve different procedures or different considerations. So the most common design that I encounter is a simple pre-post design. Sometimes there is a control group. Sometimes there is a historical control group that's used. Sometimes we have a randomized controlled trial. So people are randomized to an intervention group and a control group. And lastly, sometimes there's pre-post designs where there's no control group, and you just want to see if the change over time within one group is significant or not. Now, it's always better if you can include a control. However, sometimes you're limited by just feasibility. Sometimes you can't have a control group. So even with a most common design that's pre-post with no control group, talk to a statistician to see what you can do to arrive at the best, most valid conclusions. Finally, you can go all the way up to some pretty complicated type of models, which are whenever you have data that are clustered or nested within each other. For example, let's say that you have multiple patient notes per resident. And let's say residents are nested within hospitals and hospitals are nested within geographic regions. That could actually be a very complicated situation that you need some specific consultation, or I should say collaborative advice from a statistician. You also may have repeated measures where you have 10 time points per person and you want to look at things overall 10 time points. That's a little bit more difficult than looking at just 2 time points. Finally, we have multi-site studies where we have multiple individuals from several different sites, and we need some special procedures to be able to accommodate those. So whenever you're trying to do stuff toward the bottom of this list, consult a statistician. And hopefully we'd be able to collaborate together to produce valid results. All right, happy to discuss. And some final thoughts. Things to keep in mind. Often there are many equivalent approaches or many different valid approaches to answer the same research question. There are often lots of different tests that you can do that are exactly equal in terms of the results they give you, and sometimes they're approximately equal, but both are valid. So there's no one true solution to solving a problem in statistics. Again, notice no statistician is an expert in all areas of statistics. I may be an expert in one area, say design of clinical trials or working with claims data. Someone else may be more interested in machine learning. Some statisticians might have a true expertise in another area that I don't. So sometimes one statistician won't work for your study, whereas another one would. If you're working on focus groups or interviews, you want to talk to a qualitative methodologist, not a statistician. A qualitative methodologist will help you work on how to do qualitative analyses, not covered by statistics. And finally, if you're looking for some expertise on survey design, a psychometrician is someone that you can reach out to. And if you're not sure who to contact, you can reach out to me first, and I'd be willing to point you in one or several great directions. All right, so that's actually all that I have. My information and emails right there. And I see that we're pretty much exactly at 1. So if there's some discussion questions that we want to go over, I'd be more than happy to.
That was great. Thank you. I think I echo Ling Lin had to leave, but she said this would be fantastic for our fellows, and we have the recording here. So that was wonderful. Kanthi, I see you're still on. Do you have a question?
No, I just want to say thanks to Scott too. This was, sometimes you feel like we know all this, but a nice refresher like this just brings that back. And yeah, I think it's really important. I agree with what Noel and Lynn said, that I think it's great for the fellows. And I know you did some of this for us too, but I feel like this is something ongoing. If they have this as a resource, as they even begin to plan their projects, I think it'll be really of great help. So thank you for doing this.
Of course, of course. And I guess one final thought that I could add to this is that sometimes statisticians themselves forget to do these steps. So this is a guide for statisticians as well. We're often a little too code happy and forget to look at our data first. So, it's not just unintentional mistakes that are made from investigators with the research question. Sometimes statisticians can make these mistakes too. So it's good for us to have the checklist as well.
Wonderful.
Thank you. One quick question, if you have a second, Scott.
Sure.
As CTSI stopped supporting medical education research, I had mentioned in the middle of the talk that we desperately asked our vice chair of clinical research to help, and he got together who we actually have based on grants here, and they said that depending on the volume, they'd be able to help. But what are the services that you could potentially provide? And I guess that would be, you'd need funding from the team here, which I don't know how we get that, but what's for your group services, what's the workflow for that?
So it all depends on what the scope and the needs of your study are. So at the data center, we have services that do range from qualitative services to faculty that specialize in psychometrics, as well as lots of biostatisticians. Now, when working with us, you would typically work with a faculty member who would guide the collaboration. And often you would have a master's level statistician also working with you in some capacity to be able to check results that you obtain yourself based on discussions with me. And sometimes if it's a really sophisticated analysis that's beyond your scope, a master's level statistician would be able to do some of that work. And in terms of the workflow, it all depends on the scope of the project. It's hard to really pin down exactly what the workflow is. However, you can reach out to me or go to you can go to the CRHC website and get contact info. We have a project intake form in which you can actually specify details of your project and what you're looking for. And I'd be happy to send the specific link for that as well.
Yeah, that would be great if you could send that to Savannah. And I know it's probably just based on what your answer is. It's such probably a big range of what the funding needs would be for that. There's sometimes small funds available. I mean, what would the range be in terms of typical small to medium project funding? What would a range be? Just so I have
for like a medical education project, let's
Yeah.
say it's like evaluating an intervention and looking at pre-posts and possibly even involving a control group. And it doesn't get too down the rabbit hole of scary statistics. A typical range may be about $5,000. That's often a benchmark. Sometimes whenever you extend it to more analyses and include more outcomes, more ways of looking at the data, the budget can go up, and I've seen budgets that reach up to 10,000. Now I know that does sound expensive. However, that is reflective of the rates across data centers in the United States, and they're also comparable to other data centers within the University of Pittsburgh. So might seem like a lot, but you would always get a cost estimate before we did anything.
Right. Okay.
Create a
That's
budget.
helpful to know just for the ranges. That does help me advocate here. So thank you so much.
Yes.